about Flexoelectric fluid membrane. I'm a PhD student. Also, I want to say welcome to the high school students. Before I start, I will briefly walk you through what I'm going to go through. And this field that I'm going to introduce, it's let's say it's an interdisciplinary area, which means that so far you have the talk about relativity, gravity, quantum mechanics, but this one is the application of geometry and mathematics and physics in the life science. And please don't hesitate. If you have any question, stop me, I'm gonna answer. I'm going to go through the introduction firstly by telling a little bit about the folding phenomena. Everywhere in the nature you can see folding that has happened, and then understanding the folding phenomena, it helps us to understand the very complex shape that it happened in nature. As a couple of examples, you can see the cerebellum in the brain, and then another interesting structure in the world is mitochondria. I don't know whether you are familiar with mitochondria or not, but the structure is very interesting in terms of having a double layer membrane. There is one membrane, and there is inner membrane that is folding inside the mitochondria. That is actually life science. It has a complicated structure also. And then the question that we might ask is, why this folding happened? There are two possibilities. One of these possibilities is maybe because of the reorganization of the mass due to growth, or by buckling because of external forces or constraints that they act on the system. Now, as a simple example of such a structure, I'm going to go through a simple system that it shows such a kind of folding phenomenon. We consider as a system a sphere, and then there is another sphere inside, let's say a sphere and another membrane inside the sphere, and there are double layer membrane that we are going to check the deformation of the free membrane to see what kind of shape they can have. And then we put the system in electric field to consider the effect of electric field in such a system as well. So firstly, let me introduce the membrane, or this kind of system that we are working with. This kind of membrane, let's say, they're built by a very, let's say, the molecules that they call a lipid membrane, or they're built by lipids. And these lipids, they have a very interesting characteristic. They're built by two different parts. One part of this lipid, you can see, okay, let's say, you can see the head of the lipids that they love water, and the tail of the lipids, they hate water. Which is why when we implement them in the aqueous environment, they start to run away. The tail start to run away from the water, and they gather together, and then they build a lipid membrane, or bilayer membrane. So this is the, let's say, membrane that I'm going to work with, and then we will get closer to the characteristic of such a membrane. We named them, in terms of physics, fluid membrane, because these lipids, they can easily move around other. So in terms of their tangential plane, they are fluid, which is why they are fluid membrane. Now, in terms of mechanics, or let's say the application of physics in such a membrane, they have some characteristic, or let's say they have different properties. The first property is that they can have, these lipids, they can stretch. So, and then stretch costs energy, let's say, and then we can calculate the area energy of such a membrane by having their surface tension pretty easily. They can bend also. By bending this membrane, it costs energy, because the hydrocarbon chain, it costs energy to just stretch. Which is why bending also costs a lot of energy. And it's so we can go through it by application of geometry. Shear energy, it costs nothing because these lipids are easily moved around another. Now let's look at the cut of the system that I was talking about. We have a confinement. It's shown here by a black circle. And there is another membrane inside the confinement that it shows by colorful curve. This is free membrane, and the other one is confinement. There is two properties that we give the system. We introduce the scale volume or reduced volume of such a system. I mean, the reduced volume, which means that the subtraction of the volume of these two membranes by the volume of the cavity or confinement, and the scale area is total area of this system with respect to area of the confinement. We scale everything here because I'm going to work numerically, which is why everything that you can see here, it's just a scale. And this example is the radius volume 0.8 and the area a little bit more than 1.2. Now let's a little bit introduce flexoelectricity and see what does that mean. There is a characteristic for the membrane, or let's say for the flexoelectric membrane, which means that deformation, if we have a surface and we bend them, this bending can induce electric field, or electric field can bend the membrane. So they have a mutual relationship, and my aim, or our aim, is to put the system in an electric field and to see the deformation, the shape deformation of the free membrane. This is a schematic figure of this kind of membrane. So this is a confinement, the ones that it has mesh, and then this one is the free membrane. And okay, the electric field, as one of the examples, it can consider as a just uniform electric field, and it has some properties that I will not go through it. So this is I think this is the only equation that I have here. So what do we do that? By considering the mechanics of this membrane, we just can write the total energy of such a system by considering the bending energy, which is, this term is the bending energy of the system. C0 is spontaneous curvature, kappa bar saddle plane modulus, that it's here in the Gaussian curvature, and then sigma is surface tension. This term actually is related to the stretch energy of the system. This term, these two are related to the bending energy of the system, and this one, this term, it's related to the electric field, or it's the energy that exerted on the membrane by electric field. And this term is the pressure differences between the inner side of the membrane and outside of the membrane. And then there is a term, so this is applied electric field that we have. N is normal, vector, pressure, and then T, it's a very interesting flexoelectric constant. It's here, and this is related to the material that we are working with. This parameter D can be negative or positive. Oh, we have just 5 minutes. Well, I'm going to just not tell you what we do, just I'm going to go through briefly to the result. By applying the sophisticated framework or geometrical framework, we can easily solve such a kind of system. They are very complicated, but by parameterization, we can very simply solve such a kind of complex system very easily. The bending energy, now it is this little term, and it's related to the curvature of this sphere. There is a curvature in the meridian that is shown by psi dot, and psi is a new parameter that we define here. And then the parallel curvature, it will be this curvature. So by having these two curvatures, you can find the mean curvature of the system very easy. And then, okay, not very easy, but it's in the simplest way that you can do that. And then the area energy and other terms. And then we connect this new parameter by the Lagrange multiplier that it is, I'm not going to go through the details. This is the pressure term and this is the flexoelectric term. And then this term, now I just define another scale parameter that is related to electric field and D also. Let's see, okay, here you can see to solve this kind of energy, the energy that I show it to you is highly nonlinear, so there is no analytical solution for that, which is why we applied two different numerical methods to this system to check the shape deformation, or let's say the behavior of the membrane. One of these methods is halfly numeric. It's by renaming that Runkuta solution, but it's complicated than Runkuta. And then by applying these methods, so you can see the behavior of the membrane, so some parts, and then another method that we apply for this system is fully numeric, that it is finite element simulation. It's a start from the very initial mesh. We have a mesh, 2,500 nodes, they connected to each other, and then we subdivide, we go through the division of the surfaces, and then we we start from the triangular mesh, and after time step, we let the system to equilibrate, and then in a way that the system, it doesn't move anymore. And then at the end, this is some solution of the simulation, so we see different type of shape or the deformation for the system, and then at the end, we compare these two, let's say, methods together, because each of them, they have advantage and disadvantage to go through the final result. I'm not going to talk about the result, but this is morphological phase diagram that we already achieved. And then I'm going to just show you a simple animation in this area. This is the morphological phase diagram, radius volume versus radius versus the scale area. And then in these places, this area, we have enough area to gather to the volume, and then we are going to see self-contact of the membrane, or a stomatosized side, let's say, deformation that is shown here in this, let's say, animation that is our free, let's say this is our free membrane, and then we walk through inside of this membrane to see the deformation. Okay. If you have any question, please.
Okay. There is one more question.
Sure. This is the inside. I mean, the confinement is not here. Yes.
Can you also somehow envision that is the process of first time a living cell was happening and has its own membrane around?
Maybe, but we are not there yet. I mean, we're looking really far away from the cells and, let's say, life science, because cells are more complicated than this simple system or modelizing that we apply.
This is also complicated.
Yeah. This is complicated?
Yes.
Okay. So any other questions?
So, let's clamp